All right, let's jump right into this explainer. Today we're exploring a seriously mind-expanding concept, one that could, no joke, literally break the internet. We're talking about something so profound, so deeply woven into the absolute fabric of mathematics, that it has the potential to completely upend our modern digital reality. We are looking at the Langlands Program, a framework that many of the most brilliant minds alive call the grand unified theory. You know, to really wrap your head around the sheer magnitude of this, I want you to imagine two completely isolated worlds of math. Think of them as two distant islands, right? And they're separated by this vast, seemingly uncrossable ocean of the unknown. For literally centuries, scholars believed that the language spoken on one island had absolutely zero relation to the language on the other, just fundamentally separate disciplines. But what if they aren't? What if there's this massive secret tunnel connecting them right underneath the water?
Well, mathematicians are currently building exactly that. They're constructing a metaphorical bridge of everything, which we call the Langlands Program. This isn't just a side project. This is a massive, generations-long collaborative effort to prove that these incredibly distant fields of math are actually two sides of the exact same coin. It is, without a doubt, the ultimate quest for mathematical unity.
Section 1. Number theory meets harmonic analysis.
Now, the specific islands we're trying to connect here are two of the most complex realms of human thought. Over on one side, we've got algebra and number theory. This is that discrete, rigid world of integers. It fiercely guards the ancient, deep secrets of prime numbers, the fundamental building blocks of math. But then on the other side, we have harmonic analysis. And this is entirely different. This is the continuous, wavy world of complex functions. We're talking about the mathematics of vibrations, kind of like the sound waves coming off a guitar string or the continuous ripples in a pond.
Section 2. L functions. The math DNA.
So, you might be wondering, how on earth do you link these wildly different universes together? How do you connect the totally unpredictable, jagged jumps of prime numbers with the smooth, continuous flow of waves? Well, in our deep dive into this topic, we find the answer in something called L functions. You can really think of L functions as the underlying mathematical DNA shared by both of these worlds. Just like human DNA carries the core instructions for life, L functions translate the rigid language of number theory perfectly into the fluid vibrations of harmonic analysis.
And honestly, this brilliantly illustrates the core magic of the entire Langlands program. Because if you can decode those continuous waves, if you actually learn how to read the vibrations of these complex functions, you can unlock the rigid, seemingly chaotic secrets of the prime numbers. The primes are literally hiding inside the waves. How crazy is that?
Section 3. The ultimate prize. The Riemann hypothesis.
Okay, let's look at the real-world stakes here, because this definitely isn't just some abstract chalkboard exercise. Solving the Langlands program would ultimately unlock the Riemann hypothesis. For those who follow this stuff closely, this is one of the legendary Millennium Prize problems. It's the Mount Everest of mathematics, right up there with P versus NP and Navier-Stokes. But Riemann is arguably the most consequential one for our day-to-day modern lives.
Now yes, the Clay Mathematics Institute is literally offering a cool $1 million reward to anyone who can solve the Riemann hypothesis. But honestly, the true value of this discovery is almost incalculable. That $1 million is basically just pocket change compared to what the solution actually controls.
So the Riemann hypothesis essentially maps out the critical line where the non-trivial zeros of the Riemann zeta function lie. And if that sounds like a bunch of heavy jargon, just take away this one key fact. Proving Riemann via the Langlands program gives us the definitive master map to predict exactly how prime numbers are distributed out to infinity. We would finally fully conquer the primes.
Section 4. Breaking global encryption.
And that brings us to why this theoretical bridge has the power to shatter the modern world, affecting every single one of us. Today, global RSA encryption, which is the exact thing securing your credit cards, your banking apps, your private emails, it works on a surprisingly simple premise. You pick two massive prime numbers, let's call them P and Q, you multiply them together to create an even more massive number, N, and you use that resulting product to lock up your digital data.
The complex modulo math behind RSA encryption relies entirely on one fundamental blind spot, and it's this. It is impossibly hard for a computer to work backward. If I just hand you that massive number n, it would take our current supercomputers thousands of years of brute force guessing to figure out which two original prime numbers you multiplied together to create it. That computational blind spot? That is exactly what keeps your bank account safe right now.
But here is the grand unified threat. If the Langlands program actually gives us the mathematical DNA to perfectly map prime numbers, that blind spot completely disappears overnight. We would suddenly hold a master key. If we can easily factorize those massive numbers, it instantly shatters RSA encryption. Literally every locked door on the internet suddenly swings wide open.
To put the sheer difficulty of this into perspective right now, there have been massive bounties in the past, upwards of $50,000, awarded just to factorize a single 200-digit number. Just one. That is how hard it is without the Langlands program. So imagine the unimaginable value and the chaos of breaking the entire theoretical framework all at once.
Section 5. Join the mathematical frontier.
Let's take a collective breath here and look at where we go from all this. We've just traveled from abstract harmonic analysis straight to the cybersecurity of your bank account. And it leaves us with a massive, looming question. Will the bridge of everything actually be finished in our lifetimes? And much more importantly, what happens to the safety of our entire digital universe when mathematicians finally lay the final brick of the Langlands program? Are we truly ready for a post-RSA world?
If these deep dive explainers are expanding your mind, and you want to keep exploring the absolute cutting edge of the mathematical frontier, don't miss our next breakdown. We're decoding the universe one notebook at a time. Be sure to subscribe right here on the Robo For Education YouTube channel for our weekly deep dives. Also, follow our Substack, site, and blog to dig into the full source documents yourself, and jump into our Discord to chat with fellow math explorers. Let's keep decoding the universe together. Catch you all next time.